Can you solve this multiplication problem fast and accurately? Looks impossible to do quickly, right? For centuries, people struggled with massive calculations, especially astronomers, until one clever idea made everything simpler, faster, almost magical. That idea is the logarithm. And by the end of this series, you will be able to do calculation that once seemed impossible. Welcome to Cosmic Killers. Today we will uncover the true colors of logarithm. To understand logarithms, we have to go back all the way to one of the basic of math, addition. Everyone knows addition. 5 plus 3 equals to 8. 7 plus 7 equals to 14. Nothing special, right? But what if we keep adding the same number over and over? It starts to get a little long. So we ask ourselves, is there a faster way to write all these repeated additions? There it is. We have invented multiplication. It tells us which number we are adding and how many times we are adding it. Remember, learning multiplication table as a kid, we didn't just memorize them for fun. They are a neat way to represent repeated addition. For example, instead of writing 12 plus 12 plus 12, we can write 12 times 3. And you don't need to add 12 three times. Just look at the table and you instantly know it's 36. That's how multiplication become a shortcut for repeated addition. But what happens when we repeat multiplication just like repeated addition? Let's try 3 times 3 times 3. That's 27. Instead of writing 3 times 3 times 3 every time, we can write 3 raised to the power 3. That little number up top, called an exponent, tells us how many times we are multiplying. This is where the magic starts. Multiplication becomes exponentiation. And with exponentiation, we unlock new rules. For example, verse 3 raised to the power 3 times 3 raised to power 2. That's 3 raised to power 5. So a raised to power n times a raised to power m equals to a raised to the power n plus m. And division 3 raised to the power 5 divided by 3 raised to the power 2. That's 3 raised to the power 3. So a raised to the power m divided by a raised to the power n equals to a raised to the power m minus n. These exponent rules are extremely powerful. Now, you might be thinking, how does this help in real calculation? Let's take a big example. What's 1024 times 256? If you know that 1024 is 2 raised to the power 10 and 256 is 2 raised to the power 8, then the multiplication becomes 2 raised to the power 10 times 2 raised to the power 8, which is 2 raised to the power 18. Easy, right? But here's where exponentiation starts to break down. To get the final answer to 2 raised to the power 18, you still need to know its value. And unless you are a human calculator, you probably don't. That number is 262,144. Sure, you could look it up in a table, but how many numbers can you memorize? How big can your table get? That right there is the limitation of exponentiation. Now the story of logarithm starts. In 1614, a mathematician named John Napier published a book with a dramatic Latin title, Translation, a description of the wonderful canon of logarithms. And that book contains the deep curiosity of John Napier. He wasn't satisfied with how slow and painful calculations were, especially for astronomers and navigators. He kept asking himself a radical question: is there a way to make calculation easier? And he found logarithm. A logarithm is basically the inverse operation of exponentiation. For example, in exponentiation, we ask, what is the result of 2 raised to the power 5? In logarithm, we ask, which power of 2 have value 32? Mathematically, log base 2 of 32 is 5. That's the same as saying 2 to the power 5 equals 32. Now you might ask, does this really help in calculation? And sadly, not at first. Napier's original tables were certainly a marvel, but they were awkward to use. His logarithms weren't based on the familiar powers of 10. They followed a complex system, a bit like a foreign language. They were also huge and often required interpolation to find values between the entries. But his contemporary, Henry Briggs, changed the course. Briggs saw the incredible potential of logarithms if they could be grounded in our base 10 number system. He convinced Napier to shift the table so that the logarithm of 10 was 1, the logarithm of 100 was 2, and so on. Briggs created logarithm tables for base 10 from 1 to 20,000, including every single number. He calculated everything by hand, figuring out which power of 10 give the value of 2, then 3, then 4, all the way up to 20,000. Later, he extended it to 100,000. Can you believe it? Every value by hand using powerful calculation method like extracting roots and repeated interpolation. But he only did this for base 10, not for any other base. In our next video, we will cover it and we will finally use the rules of logarithm to solve that multiplication problem we started with. If you enjoyed this video and want to see more colors of math and physics, don't forget to hit the subscribe button.